we're going to look at something conceptually first. So how did people first come up with an approximation of the area of a circle? We know what the area of a circle is, right?
That's circumference.
Yeah, circumference.
Area equals 2 pi r
squared.
Pi r squared. There you go. Pi r squared. Good. Okay, but let's take a look at some possible methods for doing this. So, okay, one way that we could potentially do this would be if we were to try to pinch the area of a circle between two polygons whose area we can easily calculate. Okay, so this is a square, right? So we could take a circle and let me get this. Is that about? That's probably about right. Let's see. So there's. Pretty good, huh? Don't try that at home. That's
Is that freehand?
What's that?
I said that was freehand.
Yeah, it's freehand. Yeah, that's what you learn in teacher school. Okay, so. Okay, so would you agree that if we pinch a circle between the smallest circumscribed square and the largest inscribed square, it has to be somewhere in between that, right?
Yes.
And we could even, if we know, for example, what the radius of this circle is, so that's center-ish. Okay, so there's the radius, right? Or there's the radius, right? Both of those we could call R. So what's the area in terms of R of the circumscribing? Circumscribe means outside collapsing down upon. So the black square is the circumscribing square, right? It's containing the circle completely within. The inscribed square is the blue one. That's the one that's contained completely in the circle, right? So what's the area of the black square going to be then? Okay, so it's what's the width of the black square? 2r. Okay, so this distance is 2r, right?
Yeah.
So therefore the area of the black square is going to be the quantity 2r squared, which is 4r squared, right? Everybody agree? Okay. So how about the blue one? So if we know that this is R and it's a square, then could you tell me if we made like a right triangle out of this, and this would be a 45, 45, 90, right?
Yep.
Okay, so then what is going to be the length of that segment right there? How do you get what's the magic number that relates a leg of a 45, 45, 90 triangle to the hypotenuse? What is it? Well, true. We can figure it out. But what is it?
The square root of a squared.
Square root of what?
Maybe
Say it again.
r
R over the square root of 2. Because we know in a 45, 45, 90, right? Yeah, the legs, and I could solve this, right? If I wanted to figure out what's the relationship between the hypotenuse and the legs, if I call those x, then by the Pythagorean theorem, doesn't this just equal the square root of x squared plus x squared? Right?
Yeah.
Which is just the same thing as the square root of 2 times x. Right? So the magic number that relates those is the square root of 2, which is bigger than 1, right? Agreed? Okay, so I would multiply by the square root of 2 to get a bigger answer, to go from leg to hypotenuse, or to go from hypotenuse to leg. What would I do? Divide, right? You got to get something smaller. So then isn't this distance right here just r over root 2? Okay, and so then the whole width must be 2 times that, right?
Yeah.
Everybody agree? So this whole width from there to there must be 2 times r over the square root of 2, which is what? What's 2 divided by the square root of 2? Square root of 2, yeah. So it's just the square root of 2r, right? So then the area of the blue circle must be the square root of 2 times r squared, which is 2r squared. So the area of the circle has to be pinched in between those, right? Okay? And it is, isn't it? Because pi is a number between 2 and 4. Okay? That's not very good, though.
No.
There's a lot of wiggle room there, right? Could we do better?
Always.
We could. Always, exactly. We could always do better. So we could do better by maybe picking a better shape, right? A square. What was wrong with the square here? Just think about this conceptually. Where are the parts of the square that were kind of wasteful, that didn't let us get a very... Yeah, the corners. The corners, it was too cornerish, right? And by cornerish, and we could even maybe define... Yeah, we could even define like an index. We could define the concept of cornerish if we wanted to. We could say that cornerish would be kind of a combination of how sharp the corners are, right? And maybe how many of them there are. The more corners we have, in a way, the better we could kind of fit the curve. And if they were not as sharp a corners,
The corner.
so say it again. Like an octagon might be a good call, right? So if we try something like an octagon. So I don't know what I've got available. I'm kind of at the mercy of what is on my Promethean board, and it looks like the best I can do is a hexagon. So we'll go hexagon. Oh, I got to make that. Well, that didn't work very well. Let's see. So I think I need to do something like this. Does that look fairly regular? Not great, but you get the idea. You know what I should do? I'm going to start with the circle. That'll make it easier. Oh, there it is. There, that's what I want. Okay. Okay, so let's try this again. Much better. Okay, take a look, please. Everybody agree that's less cornerish?
Yeah.
That's good. Okay.
I still think an octagon would have been better.
Yeah, it would have. You're right.
Can we like turn it a little bit?
Yeah, I'm going to try to. Okay, this is, I think you guys are in violation of our contract. Right? Too much talking. Well, even when you're waiting, let's not get sidetracked. Okay, so we could do better, couldn't we? Right?
Yeah.
That's much better than we had if we calculated the areas, which I won't make us do. We're too short on time. We could do it though; it's not a big deal. If we calculated those areas, what we would find is that we would more tightly restrict the areas. So we would get stuff better than, we get an answer less than 4r squared on the top and greater than 2r squared on the bottom end. So it still wouldn't be perfect though. These are less cornerish, but still fairly cornerish. So what could I do to get an exact answer? Any suggestions? Okay. I could let the number of sides of the inscribing and circumscribing polygons just get bigger and bigger and bigger. The bigger they get, the closer they're going to get to approximating a circle. And if I take the limit that the number of sides n approaches infinity, then I get an exact approximation because the two areas would converge on the actual area of a circle. Yes, ma'am? Well, because this is what we do in calculus. We did this before. Remember, if we go back to the start of the year when we first started taking derivatives, remember that the way we did that is we used limits, right? We took limits of the difference quotient. We did stuff like this, right? We did stuff like this. We said that f prime of x equals the limit of f of x plus h minus f of x over h as h approaches 0, right? And we got an exact answer, right, when we did that. When we took that limit, that gave us the exact value of the derivative. And we got that from a picture that we drew, and really all we did with the picture was something like this. And I really want you to appreciate this because this is what calculus does. This is essentially how calculus works, is we take something that's sort of a non-calculus setup. You know, we had some curve that just did like, oh, who knows, like that, let's say. And we had some point here which we were going to call x, and we had some other point out here which we were going to call x plus h, and we wanted to approximate the instantaneous rate of change at x by just calculating the slope of the secant line, right? And that's really all that is. That's just change in y over change in x, right? It's just a slope. But then what we did that was tricky was we said, okay, what if we let the distance on the x-axis between this point and this point shrink to 0, so that then the secant line collapsed to become a tangent line. And that's an awesome trick, because then we ended up with a way of calculating the slope of a tangent line, which had stumped people for centuries prior to that, right? So that's the trick of calculus. It's the very same trick that we're playing here, right? If we just let the number of sides in our polygon approach infinity, we're going to get, and we solve that, right? We do the math, so we figure out what that limit gives us. Then we end up with an exact answer for the area of the circle, right? A circle is, after all, really just, if you want to think about it this way, it's an infinigon, right? It is an infinigon, yeah. Okay.
Does the circle have like
Any questions? Yes.
does it have like infinite vertices or zero?
Well, the circle is the limit of a polygon with n sides, a regular polygon, and as n goes to infinity. So in a way, you would say it has, it's a polygon with an infinite number of vertices, right? It's much easier to just think of it as a circle. It's a smooth curve.
But if it has no segments between it, though, you can also say it means 0.
Well, yeah. I mean, it's in a sense, it's, you know, that's how, well, the answer, I guess if I had to, you know, it's kind of a difficult thing to pin down, but I would say that the best answer is infinity, because that's how we could actually come up with
The answer.
an exact area of a circle.
You can't come up with an answer with
Uh-uh. You can't. But what we want to do is something maybe a little less complicated. What our goal is going to be in calculus, and this is the other job that integration does. We've already discovered one of the jobs that it does. That's anti-differentiation, right? And we've done some stuff with that already. We've solved differential equations by playing calculus Jeopardy, which is just anti-differentiating. That's one thing that integration does, because that's another name for that is indefinite integration. But here's the other thing. So if I want to do something like I want to add up the area under a curve, and this is a useful thing to do. Like in calculus, for example, we're talking about work, right? We know that work equals F d cosine theta, right? Okay, those of you physics types. We know that if we calculate the work done on an object, all we have to do is we have to multiply the force acting on the object times the distance through which the force acts times the cosine of the angle theta between the force vector and the displacement vector. You guys are getting good at that. Get some practice in physics, right? Okay, but what happens, we've always assumed here that the force is constant, but it's usually not. Like let's say if you're hitting a softball, for example. If you watch somebody hit a softball or a baseball, you watch it in super slow-mo, what you see is that ball deforms massively, and then it springs back. But it's made of a really elastic material, and so it tends to spring back into place. So while it's doing that, if you were to measure the forces acting on the ball as it's being hit by the bat, it really doesn't look like this. If we were to measure, for example, force versus time, it's inconvenient because if we hit the ball, let's say the bat makes contact with the ball right there, it'd sure be nice if it looked like that. If immediately the force acted on the ball until the ball left contact with the bat and then it just disappeared. It was constant the whole time. Not at all what it looks like. It looks probably something more, I mean, I've seen it varies every time a little bit, but it looks something more like this. Like that. It's kind of wobbly because there are imperfections in the materials, but it starts off slow and it picks up speed, and then it, kind of, as it's springing away, the force gradually reduces, right? And so, maybe if we're lucky, it ends up looking, if it's a really well-made ball, maybe it looks more like that instead, okay? But even so, that is not, so we could instead, we could look at this, and it would look very similar. If we looked at a force versus displacement graph, so we could even change this to be D down here, and it would look very much the same. It might be slightly different, but I can't just get the work by multiplying the force times the displacement because the force varied the whole time, right? What really it means, in a calculus sense, is that the work is defined as the area under this force displacement curve, okay? And so the way we would write that in a calculus-based physics class would be like this. It'd be the integral of f ds from s naught to s final. So this would be when the ball makes contact with the bat, and there's where it leaves the bat. And ds is just the incremental distance that the bat is moving against the ball, or that the ball is moving away from the bat. Okay, so it's a whole different kind of a thing. What we're really doing here is this is the calculus way of saying we're going to add up the area under this complicated looking curve instead of this nice idealized rectangular curve. Which one is more accurate? The blue one is real life. Okay. Well, the black one is an approximation that makes the physics pretty easy, but not very accurate. If you really want to know what actually happens, which sometimes we want to do, we want to know what really is happening in that interaction, the blue curve is what actually describes what's going on. Okay. So calculus gives us a way, and this is what we're going to work on for a while, gives us a way to add up areas under curves, because oftentimes we need to know what those areas are. Okay. So how do we do that? Okay, so here's essentially what we do. And I'm going to shorten this quite a bit, because if we had more time, it's kind of cool what we do. But I think the main thing is that you understand conceptually what we do. So let's say this is going to be our curve. We're going to pick nice, easy curves to begin with. Let's pick one that just monotonically increases, so it's always increasing. Okay. if it's always increasing, and let's say we want to add up the area from x equals A to x equals B. So this is the area that we're trying to capture under the curve. Any ideas how we could maybe approximate that? What do you think we could do? Okay.
A whole bunch of boxes that get positioned in big.
Exactly. That's exactly the answer. What we can do is we can draw a bunch of rectangles that approximate the area of the curve. Okay, so what if we were to graph, what if we were to come up with, well, let's say arbitrarily we're going to break this into 4 equally spaced rectangles. Okay, so this is the area that we're trying to approximate. Let's just slice this area into 4 separate slices. Each slice we're going to approximate with a rectangle. If we base the height of the rectangle on the value of the function at the, that's 1, 2, 3, yeah, at the right-hand side of each interval, then wouldn't this be what the first rectangle would look like? So that's what we're going to determine the height of the rectangle based on the value of the function there. Right? So there's our first rectangle. Here's going to be our second rectangle. Right? Here's going to be our third rectangle, and there's going to be our fourth. And if I add all those up, that's easy to do, right? It's easy to do because I can determine what the width of each one of those rectangles is. It's easy to do, right? If I know what the width of the interval is, all I've got to do is just divide it by 4, right?
Yeah.
Everybody agree? Okay. Right? Does everybody see that?
Yes.
Okay. The height of the rectangle is also easy to do because I presumably know what this function is, right? Let's say this function is y equals f of x, and I know what the function is. Let's just say it happens to be like x squared. That's fine, right? So if it's x squared, then whatever that x value is, which I can know, all I've got to do is evaluate the function at that value, and it gives me the height, right? And so I could come up with an organized way of adding up all those areas, okay? And then I'd end up with area 1 plus area 2 plus area 3 plus area 4. We might even call those capital A sub 1, capital A sub 2, capital A sub 3, and capital A sub 4. Okay? What's going to be the problem with that area? Or not the problem, but it's an approximation, but how is it going to compare to the actual area? It's going to be too big a little bit, isn't it? We overshot it a little bit because all of the rectangles were circumscribed rectangles, right? Think of it this way. When I sliced this thing, I just dropped the top of the rectangle down until it bumped into the curve, right? Okay, what might I do to maybe get a little more accurate estimate? What do you think? Okay, so we could do the other, maybe we're going to inflate them from the bottom until they hit the curve. Yes?
Could you do that in electricity average?
Yeah, well, we'd know, we could. We could take the average, and that's going to probably be a better approximation than either one of the other approximations, right? But we'd know that it would be trapped someplace between those two areas. Agreed?
Agreed.
Okay, so let's do that. So because this is a monotonically increasing function, the height of the inscribed rectangles is always determined by the value at the left side of each subinterval, right? Because it's increasing from left to right. Does that make sense? So the height of this box is determined there. The height of this box is determined there, there, and there. And I might call those lowercase a sub 1, lowercase a sub 2, lowercase a sub 3, and lowercase a sub 4. And if I added that sum up, it's going to be a little bit of an undershoot, right? Okay, so what if you did a mix? Yeah, so that's the suggestion. We maybe could do a mix. Maybe we could say something like, well, let's just average the two, and that's not a bad idea. Okay, that would work. That would give us a better estimate. None of those are going to be perfect, though, are they? Okay. So very conceptually speaking here, can you think of a way that we could take this idea and come up with a perfect approximation, so the exact area under the curve? What happens if we increase the number of squares? We can see what happens if I increase the number of squares. What if we make these intervals, for example, half as wide? If I make them half as wide, look what happens to the circumscribed squares. I mean, you see that they get a lot better? Right, now this is the area, right? We don't, look, it's not as cornerish, right? We get these extra places that we used to overshoot by that additional area. Now we've exhausted some of that area, we say in calculus. We've eliminated some of it.
But you're still gonna be
Right.
over it.
Say it again.
You're still gonna be above it.
Still gonna be above it, and we're still gonna be below it when we do the same thing with an inscribed series, right? But if we let the number of rectangles go to infinity and take that limit, then we should push all of that extra cornerishness away. And the extra area will, as it disappears, the now infinitely, how do I say this? The rectangles which are now approaching a width of 0 are gonna fit perfectly underneath this curve. And the two versions, the two answers that we get, what we started off with as the blue on top and the red on the bottom are going to converge on the same exact answer, aren't they? You get the idea? Okay, so all that remains for us then is just to come up with a way of representing that. And I want to do this more quickly than we normally would. Let's just talk about how we could write this as what's called a Riemann sum. Okay, so what we're going to say here, I need to draw maybe one more picture. How much time we got?
3 minutes.
Okay, that's a great place to stop for today. So you got the idea, right? Now, here's kind of the plan. So I'm going to take one more day, and I want to just kind of talk you through how we could organize this as a discrete sum, so using like a sigma notation. We're going to add up a discrete number of rectangles. Then our strategy is going to be, let's let the number of rectangles go to infinity, and that's going to give us an exact answer. And then at the end of the story, so you kind of see the lights at the end of the tunnel, we're going to be able to draw a direct comparison between the outcome of that process and, it's really bizarre, and the anti-derivatives that we did the other day, which is just a miraculous, kind of super cool synthesis here. That things work out, so there's an awesome shortcut that prevents you from having to do this long process every time you want to add up an area on a curve. Okay? And then it ends up being something that, that it's relatively simple to do. Okay? All right.